Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Kaizman Hakimi bin Abdi. My matrix number is 212414. So today we from group 9 we present about application of differentiation in electrical principle. Next, for differentiation in electrical principle, our group has choose two application, which is circuit analysis and transmission line. Next is circuit analysis. This slide shows the circuit diagram, which is RLC series circuit that are consisting of a resistor, inductor, capacitor that are connected to the AC generator that supplies a total voltage at some instant. Okay. Next, to realize the RLC series circuit in a second order differential equation, the Kirchhoff voltage law must be applied to the circuit. The equation that we get is ET equal to VL plus VR plus VC. Okay, another terms of the equation is VR equal to IR, VC equal to Q over C, VL equal to L di over dt, and I equal to dQ over dt. Next, we substitute the term into the equation. We get ET equal to L d square Q over dt square plus R dQ over dt plus 1 over CQ. So this equation is modeled as the second order differential equation.
Hi, Assalamualaikum. My name is Muhammad Zulfakri and my matrix number is 210347, and I'm going to explain the example 1 of application RLC series circuit. So based on the question, we have ET is equal to 150 volt, a resistor of 10 ohm, an inductor of 1 Henry, and a capacitor of 1 over 1900 farad. And the question asks us to find the charge on the capacitor at any time with the initial current and initial charge is 0. So number 1, we need to substitute the data given in the second derivative of the equation of RLC, and we get this as the answer. This is non-homogeneous equation, so we need to equate to 0 to find the homogeneous part, and I changed this equation in the quadratic form so that we can find the value of Q by using the completing the square method. And at the value of Q, we have two parts, which is the real part alpha and the imaginary part beta. Then we substitute those values in the general formula of QC, and we will get the value of QC with two unknown variables A and B. Next, assuming that QP is a constant of C, so Q prime P is equal to 0 and Q double prime P is also equal to 0, substitute in the non-homogeneous equation to find the value of QP, and we will get 3 over 38. Then calculate the value of Q by summing up QC and QP, and this is the equation that we have with two unknown variables A and B. So to find the value of A and B, we need first to derive the Q equation, and by using the product rule, and this is what we get. Now, find the value of A and B. Since Q not equal to 0, substitute Q equal to 0 at initial point T equal to 0 in equation Q, and will give us the value of B, negative 3 over 38. Since I not equal to 0, substitute I equal to 0, B equal to negative 3 over 38 at initial point T equal to 0 in derivative equation of Q, and we will get the value of A is equal to negative 3 over 193, and substitute those values A and B in the general formula of Q, and we will get the final answer of the particular solution, the charge on the current on the capacitor Q. That's all for me. Thank you.
Hello, my name is Diven Parthiban, matrix number 213058, and today I'll be explaining about the methodology of transmission line. As we can see in this figure, transmission line consists of 2 points. One is the sending end and one more is the receiving end. A cable of L kilometer in length carrying electric current with instantaneous voltage Vxt and current Xt at any point distance x kilometer from sending end 0 and at time t per second. Now between point P and Q, we call it delta x, and in this point occurs voltage drop and current loss. To calculate these two voltage drop and current loss, we use two formulas. First formula is to calculate voltage drop, which is given by voltage drop due to resistance plus voltage drop due to inductance, which is negative delta V equals to IR delta X plus L del I over del T delta X minus negative del V over del X equals to RI plus L del I over del X. To calculate current loss is given by current loss due to capacitance plus the current loss due to leakage.
Bismillahirrahmanirrahim. My name is Hash Suleiman. Let me continue the example of the transmission and how the derivative help us to derive the equations to get a voltage wave traveling forward and backward at the same time in the transmission line. So as we can see here, this is the equation, second derivative equation, equal to gamma squared V. So the voltage is in terms of space and the time. So this is a gamma, it's a propagation constant. So as we can see here, this gamma is equal to alpha plus beta j. So alpha is the attenuation constant, whereas beta is a phase constant. So we can assume this as lossless transmission. But actually this equation is saying that is the voltage with the flow in the circuit, or we can say the voltage going to the transmission line, it has the nature of the transmission wave. So the wave is traveling like a transmission, the voltage is traveling as a wave. This is a wave traveling as a wave. The voltage is traveling to the transmission line as a wave. So this is the positive direction, what's going forward, and this is what is going backward in the transmission line. This equation we can get the transmission line, or the travel of the voltage traveling to the transmission line backward and forward.